Okay then. So we will begin last night. So yeah, Shivangi, can you share the screen and start?
Yeah, sure. Can I take 2 minutes? Just 2 minutes.
Okay, okay, fine. In the meantime, good evening everyone. So today we have a student presentation by the Theory 2 cohort of Equinox 2022 by the Planetary Nebula team. So in Theory cohort 2, we have the understanding of radio sources, so astronomical radio sources. We have radio galaxies, quasars, and planetary nebula, the three groups. So today we have the first group, planetary nebula. We will be presenting planetary nebula as radio sources.
Okay, so I'll start. Am I audible, guys?
Aywa.
Yeah, sure.
Yeah. So, good evening, everyone. We are from Planetary Division Group of Cohort 2, and I am Shivangi. Along with me will be presenting Shreya and Chinmay. So, a quick introduction about ourselves. I'm in first semester of my engineering, and these two guys are in their 12th grade. So today we'll be presenting on Butterfly Nebula, something which we are working on in cohort 2. So now I'll present my screen. Is it visible, guys?
Iris.
Yeah, sure.
Okay, thank you. So here's an introduction to Planetary Nebula. So it's one of the stage in the life cycle of a star, and it comes just after the red giant stage. And here is here is a picture of 6 planetary nebulas. So the first one is NGC 6302, and this is the Butterfly Nebula, and this is the one which we'll be discussing in detail. And then there's the second picture is there. It is the IC 418 Nebula, and it is also called Spirograph Nebula. Then comes the third nebula, which is NGC 3242. This is called the Ghost of Jupiter Nebula. Then the fourth one is NGC 7662. This is also called Blue Snowball Nebula, and this is located in constellation Andromeda. Then comes NGC 7027. This is Jewel Bug Nebula, and this is in constellation Cygnus. And the last one, as you can see, is the NGC 2371, and this is called the Dual Lobe Nebula, and this is in constellation Gemini. You can actually see the two lobes of the NGC 2371. Then coming to the physical characteristics of a planetary nebula. So in general, it is roughly 2 light years across in dimension. Coming to the density part, it ranges from 100 to 1000 particles per centimeter cube. And as the nebula ages, due to expansion, the density decreases. So talking about mass, it ranges from 0.1 to 1 solar masses. And the temperature of the gases at the periphery of the nebula is 10,000 Kelvin. And when it comes to the temperature of gases in the central region, it is 16,000 to 25,000 Kelvin. Now, talking about morphology, so basically most of the planetary nebula we find are in spherical, elliptical, or in bipolar shape. So, so this bipolar nebula are concentrated in galactic plane. Now, the galactic plane is the plane on which majority of the disc-shaped galaxies mass lie, and these are produced by young massive progenitor stars, the bipolar nebulas. On the other hand, the spherical nebula are produced by old stars similar to Sun. So the different shapes of nebula is due to gravitational interactions with the companion star in binary star system. Now coming to the formation of a planetary nebula. So the first planetary nebula was discovered in 1764 by a French astronomer Charles Messier. And so basically, when a star is a red giant, it spins slowly and blows off a dense but slow solar wind. If there's nothing else happening to the star, then that wind will blow outward in all directions spherically. However, all those outer layer of the star peel away and they expose the deeper, hotter part of the star. The star starts to blow at much faster but far less dense wind. That wind catches up with and slams into the slower wind. So here in this video, I'll show you guys. So now if a dying star has a companion, they may circle each other rapidly. That will shape the wind, forcing more of it outward in the plane of the star's orbit due to the centrifugal force. When the fast wind kicks in, it slams into that stuff in the orbital plane and it slows down. But there's less stuff in the polar direction, up and down, out of the plane. So it's easier for the wind to expand in those directions and it forms huge lobes of material stretching for trillions of kilometers. So this is how planetary nebula get their shapes. Now there's one more thing. So here in this video you'll see. So there's a possibility that maybe the stars had planet like in our own solar system. So if the star expanded into a red giant and swallowed them, it would take millions of years or more for the planets to vaporize. And for all that time, they would be orbiting inside the star, moving faster than the star itself. The planets inside the star would spin it up, causing it to rotate faster, fast enough to explain the shapes of planetaries. So this is why we see many weird and fantastic shapes in planetaries. So what happened in nutshell is their progenitor stars swallowed their own planets. So yeah, talking about the lifetime of a planetary nebula, it's very short actually. It's between 10,000 to 20,000 years. And the formation of planetary nebula thing starts just after the AGB branch phase. Now the AGB branch phase comes just after the red giant phase. So here I'll explain. So this is the HR diagram, and HR diagram stands for Hertzsprung-Russell diagram. And the blue color dots you can see are the stars which are currently in the AGB phase. And this AGB phase is just before the formation of planetary nebula, as I already explained. And it's a lower intermediate mass star at its late evolutionary phase, which appears like a red giant. So for more information, this red colored or maroon colored dots you can see. So these are the dots which represent the stars which are in lower RGB phase. So RGB phase stands for red giant branch. Now again, the orange colored dots represent the upper red giant branch. Similarly, the yellow colored dots represent the horizontal branch, and the green colored dots, which are very few, represent the RR Isaac variables. Now, yeah, coming to our main topic, which is Butterfly Nebula. So this is how it looks. You can see it here. And so So Butterfly Nebula is also called Bug Nebula, and it's bipolar in shape. By bipolar, I mean that there are two lobes on either side of the central star, and the central star is very, very hot. Now, this nebula lies in the Scorpius constellation. So, here is the location of the Butterfly Nebula given. Already told, it lies in Scorpius constellation, and the arrow here shows the location. Also, this nebula is in our own Milky Way galaxy, and it's just like 3,800 light years away from Earth. And there are other planetary nebulas in Scorpius constellation as well, as you can see here. This green thing you can see is the 633 NGC 6334 nebula. This nebula, which is actually quite big and just beside the S of the Scorpius, this is NGC 6357, and this is also called the War and Peace Nebula. So moving on. Now coming to the formation of Butterfly Nebula, which is also kind of the problem statement of today's presentation. So the star first evolved into a huge red giant with a diameter of about 1,000 times that of our sun. Now, for the reference, the diameter of the sun is 1.3927 million kilometers, and this star was actually 1,000 times more bigger than our own sun. It then lost its extended outer layers. Some of their gas was cast off from its equator at a relatively slow speed, perhaps as low as 32,000 kilometers per hour, creating the donut-shaped ring. Other gas was ejected perpendicular to the ring at higher speeds, producing the elongated wings of the butterfly-shaped structure. Now later, as the central star heated up, a much faster stellar wind, a stream of charged particles traveling at more than 3.2 kilometers per hour, plowed through the existing wing-shaped structure, further modifying its shape. So the nebula's reddish edges are largely due to the light emitted by nitrogen, which marks the coolest gas visible in the picture. So, so yeah, these are my references, and I would like to end my presentation, and I would like to hand it to Chinmay, and he will, no, maybe Shreyasi will continue it from here. So I'll stop sharing now.
Okay, am I audible?
Yeah,
Yeah, you
you
are.
are.
All right. Uh, is it visible?
Yeah.
Okay. Good evening, everyone. My name is Shreyashi. So we will be talking about the size and dimension of Butterfly Nebula, which is known as NGC 6302. I really think this is very important to know as well as interesting. So let's move forward. So we were talking about the size or radius of NGC 6302. Its radius is 1.50 light years approximately, and since one light year is equal to 9.5 trillion kilometer, we can take an estimate that its radius is about 14.25 trillion kilometer. Its diameter is about 3 light years, so of course it is very fast stretched. As you can see, this would be the radius of the nebula, which is 1.50 light years, and this would be the diameter, which is approximately 3 light years. Now, coming on to the angular size, the angular size is given in arc minutes, which can be roughly turned into light years. So we can take the unit as light years. So 0.767 is the major axis of the object, that is the length, and 0.767 is the minor axis of the object, that is the width, which is like both are kind of the same. So the major axis is this one part, and the minor axis is this one part. We can take it kind of like a square thing, since both of the length and the width are same. And at the middle, there's a perpendicular form, which is the 90-degree angle of orientation, which is this middle part. So it forms the 90-degree angle. Now let's sum up the size and dimensions of NGC 6302. That is the Butterfly Nebula. Distance of nebula from the Earth is 3,800 light years. And we know that one light year is approximately 9.46 into 10 raised to power 15 meters. Therefore, doing the calculation, we get that the NGC 6302 is 35.948 into 10 raised to power 12 kilometer far from the Earth approximately. The radius is 1.50 light years. The angular size in arc minutes is 0.767, 0.76790 radian. And the dimensions of NGC 6302 is about 2.25 arcmin across, that is about 2 light years. So the reference is given below so that you can refer here for more details. That is the universeguide.com, and it has a lot of the facts about the size and dimensions, and we can find like the information from the hubblesite.org. So yeah. Now coming on to the color composition of NGC 6302. Not gonna lie, it does look so fascinating and beautiful. So let's see how the color composition actually works. First of all, let's talk about its color information. Like, where did we acquire it from? So basically, it was acquired by Hubble Space Telescope using separate exposures by WFC3 UVIS, that is the ultraviolet imaging spectrograph, and WFC3 IR, that is the infrared radiation. And several filters were used to narrow various wavelength ranges to find appropriate composition. There were like different colors assigned to different hues, colors, and brought to monochromatic, that is the grayscale image, associated with the individual filter from the different hues. So like different filters were assigned to it, like different colors were assigned, and then it was converted into grayscale, and then we could just identify like what type of color was actually, like what is the color information there. Now, we would of course like to know what is the assigned colors that we were talking about in the previous slide, like the assigned colors of the different hues. So total of 5 colors were assigned, which were purple, that is namely F502N. Then it is luminosity, namely F656N, and it's kind of like grayish here, but usually the infrared radiation that was used is the red, but it's I think it's kind of dim. So next is green, that is namely F6589. Then next is cyan, namely F110W, and orange, namely F1649. So this is the most clear image of Butterfly Nebula taken from the assigned colors. So the narrowband imaging was used here. That is like these kind of imaging was used so that we can identify which colors were used here. So oxygen triple I emits, like oxygen 3 emits 495.9 nanometer and 500.7 nanometer, and it is a blue-green colored filter, which is, we can see here, kind of like blue-green colored type things, which we can identify as the O3. And then coming on to H alpha, that is a specific deep red visible spectral line with wavelength of 656 nanometer, but it's kind of like we can see here the thing which is like kind of luminosity like color, but it's actually kind of red, but we cannot see, like it's not that much prominent here. Next is wide H alpha and N2 that emits a kind of greenish filter, and similarly the YJ as bluish and F2 as orange. For more info, you can refer to the hubblesite.org website, and you can find more details about what I'm actually talking about. Now, we would of course be wondering what created this butterfly shaped effect. So the butterfly like wings of gases and dust are a common shape of a planetary nebula, and such butterfly shapes are created by the interacting wind process. So what is like the interacting winds? The fast wind material propelled by radiation from the hot central star punches a hole in the cocoon, allowing the nebula to emerge. So what does it mean? Here we can see like it kind of looks like a cocoon, and of course like when the winds hit it, and of course it would create a radiation kind of thing here that feels like it is emerging from the cocoon, that is the hot central star. So this is how the nebula actually emerges, and this is how the effect is actually created. Now, Dr. Sun Kwok is the one who proposed the theory, the interacting wind theory, and he proposed this theory to explain the origin of planetary nebula. Dr. Suncock is the Dean of the Department of Physics and Astronomy in the Faculty of Science in the University of Hong Kong. And he's so immersed into such topics that he has also been proven successful in explaining the nebula's shapes. Now, what is like the from our frame of reference, like what do we see from our perspective? So the nebula are being illuminated by light from the invisible central star, which is then reflected towards us. We are viewing the nebula edge on, where the direct starlight is blocked by the dusty cocoon. Otherwise, starlight would overwhelm the nebula light, which like make it very difficult to see the butterfly-shaped nebula. So, what do I actually mean by it? We are seeing the image from like head on, the edge on thing, and we can see the different like images that was created. If we were seeing from this side, we would just see like just a light that was being immersed and not see actually how it's actually forming and emerging. So it's from our perspective or from our frame of reference that we are seeing this kind of image. So now let's talk about the observations made using the filters. The observations were made with the wide field and planetary camera 2, which is a part of Hubble Space Telescope, and 3 filters were used. That is the yellow, green, blue, and near infrared. And the images were taken in 1997 by Suncock and in 1996 by Matt Browski. So these are the images that were taken by Suncock and Matt Browski. The IRAS 171503224 is known as the Cotton Candy Nebula, and IRAS 174412411 is known as the Silkworm Nebula. NGC 6818 is known as the Light Gem Nebula, and NGC 3918 is known as the Blue Planetary or the Southern. So, of course, like the filters that the assigned colors that we discussed in the previous slides about the color composition, we can see how different colors were used and the images, and how we can like take an idea about how the nebulas would actually look like. So yeah, that was my talk, and I would like to hand over the platform to Chinmay for further discussion.
Just a minute. Just let me know if my screen is visible. Is it visible, my screen?
Yes, it's visible.
Okay. Hi, my name is Chinmay. So I'm going to explain to you the chemistry of Butterfly Nebula, including how one's chemistry is formed basically, and some basic properties of the Butterfly Nebula. We'll take a dive into the contribution of some people and some machines that worked on knowing this. Let me start with the composition of nebulas. The center section contains a carbon core surrounded by gas, cloud of gas, which you have seen in some previous images, which was shown by Shreyashi and Shivangi. So that's something to know at first. As written here, the prominent dust cloud in the center of the nebula possibly consists of mainly hydrogen, silicates, and quartz. So planetary nebula are formed from ionized gases expelled by the red giants as they approach the end of their lifetimes. This may be seen in the diagram depicting the stellar cycle, which depicts how a star is born and what occurs after it dies. To speak about the formation of the red giants, when all the hydrogen has been used up in the fusion process, large nuclei being formed and the stars may expand to become a red giant. That's how red giants are formed, basically. And when the red giants die, that's when the nebulas are created, as you can see in the picture. This is one of the most extensively used images of Butterfly Nebula, taken by the Hubble Space Telescope in June of 2022. I'll be talking about Hubble Space Telescope soon in the slides. It is kind of a recent one. This picture is kind of a recent one. This is something, the result of an analysis done by Joel Kastner, who works in the Center for Imaging Sciences at Rochester Institute of Technology. This image shows what type of chemical element composition is there in the nebula. So as you can see in this picture, red part in the middle, where the stars are present, consists of particles from text extensions. And the green In the outer part shows the ionized nitrogen, which you can see here, and the blue part, which makes an S shape from the top right corner to the bottom left, consists of ionized iron. This is the picture of Joel Kastner, who have done multiple contributions to the field of nebula imaging and analysis. Talking about this part, where the ion emission is present, which look like an S from the English alphabet series, is made up of the rotation, made by the rotation of the stars, which is present in the center. Someone who worked on this is Bruce Ballack from the University of Washington, who said, and I quote, "It's commonly observed in supernova remnants, active galactic nuclei, and outflowing jets from the newborn stars, but is very rarely seen in the planetary nebulas." So that's something unique with Butterfly Nebula, to say. One of the most notable scientists who worked on this topic is, of course, the one who discovered it. Fortunately, that's the same person who coined the term of butterfly. Sir William Herschel, whose discovery also includes the discovery of Uranus, also the infrared radiation. Also, there has been some Indian contribution from starting, and one of the most notable scientists from India who worked on is Professor Kameshwara Rao of the Indian Institute of Astrophysics, Bangalore, who worked on so many ISRO projects, such as the one I have shown here on the right side, the Ultraviolet Imaging Telescope, the UVIT, which was on board on the AstroSat, which was one of the launched few years ago. As the name says, it is something used for imaging things using the UV rays. I'd like to end my talk by acknowledging the thing which has contributed the most to the field, nothing other than the Great Hubble Space Telescope. Most of the pictures you have seen of the internet of the Butterfly Nebula must be taken by using the humongous tool, which I say is really big. It is really big. It is 13.2 meters, which is compared to with the size of a school bus. So yeah, that's something about Hubble. Now I would like to request Shivangi Didi to take over from here and give a closing note.
Yeah, so everyone, this is it from our side. We three worked on this, the Butterfly Nebula thing, and this is the presentation we made and we produced it before you. So thank you so much for letting us do this here, and thank you so much for streaming it, and thank you so much for attending this session.
Thank you, Planetary Nebula cohort. So, from the audience, is there any doubts, any comments, reviews? Is the right time to ask? If you can't unmute, you can put in the chat box, or you can unmute and ask. Okay. Is there no doubt, guys? Okay, Aditya says quick and really informative session. It was great. Thank you, Aditya. Ayush Kamal is asking, can you explain the formation of planetary nebula, like a brief note? Shivangi? So what exactly causes planetary nebula?
Yeah, sure. See, what happens exactly is so first the star is in its red giant stage, and red giant stage is actually a late evolutionary stage of a star. So before red giant, it's actually a star. When it comes to red giant, it starts losing its energy, and then after the red giant stage, the star starts spinning very slowly, and due to that spin it also blows off winds, which we can call as solar winds. So due to this blowing of the wind, what happens that the gases come out in different directions and they give shape to the planetary nebula which will be formed. So these gases come out in different forms. Sometimes it comes out from the equatorial region of the star. Sometimes it comes out from the perpendicular to the equatorial region, which is also the polar region of the stars. So due to this, lobes or spherical shape or butterfly shape can be created. So this is uh, the creation is all about blowing off the winds and blowing off of the gases which were present in the star, and and the materials and the dust, and this is how the creation happens.
I would like to add on to it. I spoke about the interacting winds in my slides, and that also plays a major role in formation of the nebula.
Okay. So any more doubts, guys? Okay, if there is no more doubts, it was a wonderful session, Shivangi, Shreyashi, and Chinmay. And yeah, that's it, guys. Thank you for joining.